Might be double stream then. No. Let me just let me just find the link now and send it. Uh mm. Oh, okay. Uh I just want the link. All right, let me check something here now. I can get participate through this one now, guys. Send. And then let me see now. All right, I see now two link. All right, take out that. All right, and putting it here. There she takes it's working. All right. All right, so I don't need to put in this one then. It's working. All right, guys. Everybody seen the YouTube link in the group?
Yes, sir.
Man, let me take it out of full screen so I can see what's happening here. But I don't think we have 10 persons. I think everybody can hold it. It's not filled. The studio is still open. All right. Let's click that one. All right, guys. So we're gonna go through that lab sheet quickly. All right, guys. All right. So it's doing Michaela, Dejane, Shantai, Giovanni, and so on. All right. So if you're joining in through YouTube, you can also participate because it allows the chat as well. So you can send a comment or something, and then yeah. Let me just say something here. Yeah. It's actually posting it from all destinations here. All right. So if you can hear us, DHNA, just send us a message. Oh, Marlon, very good. Marlon is there. Good. All right, let me just show a comment here. Marlon is there, guys. And DHNA, you there? Sorry. Let me just add somebody. Janari is in the stream. All right. DHNA, you can hear me?
Yes, sir.
Good. All right, good. I wonder who else is out there. I wonder if Benita is here. Deborah. Oh, Deborah. Yeah. Deborah is here. All right. Well done. All right. So can get everybody. All right. Dear Chanel, send a text if you can hear us or if you're participating. I can see what's happening. All right. So we're good then. All right. Meanwhile. All right. So guys, I would say if you're on YouTube, you can always just text to participate and we can deal with you there. All right, guys. So let's just go through this quickly then. As you notice, there is and hopefully you can see this clearly though. Let me get some zoom on it. Yeah, probably Let's get a bit more focus on it. All right, guys. So for this lab, lab 5, very important lab, guys. As I say, it's a compulsory lab that uh where everybody is expected to at least do some version of it. And there are different versions of this lab. You actually have we have a version where we use a dice. We have a version where we use a burette. Uh, has anybody seen this lab before? This experiment before, or has ever done an experiment with Half Life?
Yes, sir.
I
Yes.
don't think so, sir.
Don't think so. All right. Giovanni, you say yes? Somebody said yes.
Yes,
Who said yes?
sir. Giovanni.
All right. Oh, Giovanni. All right. So okay. So you did it recently?
In February.
February. Okay. Good. So that's what you girls at Hampton going on with, pushing the labs really quickly. All right. Well, this lab is actually towards the end of the syllabus, so we're doing it now. You know that we have a 1 year program, so you know that's how it works because you know, have to try and do our thing differently. But um, this definitely, guys, you know, it's a very likely question on the exam. I mean, this has been asked like on many past papers. Think if I could drag my memory a bit, 2000 and I believe it was 2017 or 2018. Um, 2 years in a row they sent a question with Half Life. So um, you know, it was something that students weren't doing well, and CXC decided that well, you know what, let's keep pressuring this topic. So so we're here now, guys. We're actually doing this lab, um, and so yeah, let's proceed. All right. So as you can see, guys, the skill for this lab is AIORR, and let's see if we can get this pen right in. This is gonna be what lab 5. Let's choose the color ink. It was on white, so can I use white to white and all right. Okay. So we have number 5 here, guys, and of course today's date is the 13th. So 13th of the 4th, 2021. All right. Remember the definition for Half Life, guys. Okay. So we're saying it looks familiar. Um, you're saying it looks familiar. All right. Yeah. So that's what her response is. All right. That's cool. All right. Still not hearing from Chanel. Is Chanel out there somewhere in the universe? Let's hope she's there. All right, so let's continue. We're going to scroll up through this, guys, and this definition for Half Life very important. So let me just bring it up on the screen so you can see this definition for Half Life. Everybody can see that.
Yeah, yes, sir. I can see.
All right, a radioactive substance, the time taken for half of the activity of that substance reduced to half of its original value. All right, so for this now we're using kinds to simulate the experiment. All right, so bear that in mind. All right, so this is it. That when you're doing this experiment, something you can do at home. So I mean, and all we can do here is talk about it because we can't really. Well, I don't have any kinds now to really do this lab, but then it's something that if you can find kinds, um, or anything like kinds, you could do this lab. And this is simulating. Well, this is cobalt 60. We learn. Did we talk about cobalt 60, guys, before? You remember we spoke about cobalt 60. All right, you guys. The only way you won't remember this is if you didn't take up your book or you weren't learning that day. But we did speak about Cobalt 60.
Yes, sir. I did
Uh,
have a comment.
yeah. So what you remember about Cobalt 60, January? Because it's likely if this were to be
What
a
remember
question.
about it, sir?
Yes. What is cobalt 60 used for?
I think it's used for. I think it's used in some medical something or some area that
Yeah,
aspect
certainly.
use it.
Yes, it's used in medicine. All right, and you seem to be the only one that remember that. What about the persons online? What about the persons on YouTube? And
Sir,
it
it's used to treat cancer.
okay, yes, Luyan, yes, yes, very good. Used specifically to treat cancer, yes. So Janari had the idea that well, it's used in medicine, but then definitely going one further and saying that it's used to treat cancer. Yes, so cobalt 60 is a cancer treatment isotope, radioisotope. All right, so radioisotope, all right, used in medicine. I hope everybody remember that radioisotope used in medicine, all right, for cancer treatment. All right, very good. So, all right, now this is telling you how the cobalt 60 will behave in terms of its half life. Now, you having yeah, sure, they were saying we did. All right, so yeah, cobalt 60 here. If you have a sample of well 100, and this is what the graph is showing. So understand this. This is telling you the percent that's remaining over time. But you seen that?
Yes, sir. Just as I was
Yeah.
saying, cut in half,
Mm-hmm.
sir.
Cut in half. Yeah, so we if talk
Sir,
something. All right. Yes.
like it out by half each time. Just like I show
Oh,
you on the table, yes, sir. I was
well,
talking
yeah, that's
about
it. Mm. So, but then when you say it cut in half, you have to be specific. What cuts in half? Is it the
every number is reduced down to. It's cut in half again.
okay? And what are these numbers representing on the graph? Which numbers are you
Numbers
referring to, by the
representing
way? Because there are many numbers on the graph. Which specific
the
number you're
grams
referring to?
one, sir. The
Oh,
grams.
very good. The grams, very good. So, and grams is used to measure what quantity?
Grams we used to measure what quantity? Weight
Yes,
or
what
weight?
weight?
Sir.
Grams is used to measure weight. Really? Anybody else want to interject here? What physical quantity is measured in grams?
Sir, mass.
Us.
Mass, definitely mass. So as physics students, always remember that there's a difference between mass and weight. All right, there's a difference between mass and weight. All right, that's where the physics student differs from the average person on the street. The average person on the street use the words interchangeable. In fact, they just use weight. Period. You hardly hear them say mass. Mass is not in the average person vocabulary. All right, but tell them about weight, then they perfectly understand you. But you know, that's also it is. All right, so physical quantity shown here on the graph within the circles with these dots is the mass of the cobalt 60, and of course on the y-axis it shows a percentage that remains. All right, and that's the y-axis. The x-axis now, which is the horizontal axis here, is going with the number of half-lives here. All right. Now, notice that half-life is measured in time. Is actually is a time value. All right. It takes 5.27 years for cobalt 60 to decay. All right. So, and again to half of its original value. So that is the concept here, guys. The half-life. Some half-life might be long in terms of years. Some might be short in terms of seconds. Um, I think, for example, the element francium. I believe Marie Curie had something to do with that element as well. Francium, I think, that one was named after France. So Um, that one was certainly all right. So so that one has a very short half life. I think it's seconds. If we check the Google or somewhere, it might tell you more information there. But this now, guys, is cobalt 60. After one half life, it drops. Well, it drops to 5. So you start out with 10, then it drops to 5, as Gennaro was saying, and then from 5 to 2.5, and then half of 2.5 is 1.25, and a half of 1.25 is actually 0.625 grams. Hope this is understandable for everybody. All right, so yeah, definitely. Yeah, so then the boy is interjecting here and saying, yeah, I mean, maybe these comments coming in late, but let's see what's happening. All right, guys, any questions so far? Any questions at the moment?
No, sir.
No,
All
sir.
right.
No, sir.
Dijon, are you still there?
Sir, I noticed that this thing is slow, sir.
Yes, sir.
What thing is slow?
Like when I speak, sir, like it take a little time, like a delay to respond. So I noticed that
Oh,
when I speak.
you notice that. All right, let me just check to see if all right. Yeah. Let's say point out that because if it is opened in another browser, then that could slow it down. So let me check. All right. All right, let's hope it improves though. All right. So here we go, guys. We're going to continue here. So as you can see in this experiment, you're going to use clients to simulate it. All right, let me zoom into that one. Everybody seen that here in this experiment?
Yes, sir.
All right. Somebody can read that part.
In this experiment, you will use coins to simulate the decay of the atoms in the inert radioactive substance. When the coins are thrown onto a table, it may fall on a heads or tails. Heads means that the coin has not decayed and should be counted then placed back into the cup, while tails means that the atom has decayed and should be removed.
All right,
The
stick up
coins
in
in
there.
the okay.
Stick up in there, Janari. Thank you very much for that reading. So, all right, everybody understand what is being said so far? But understand what's happening here? All right. So the kinds that you will use to do this experiment, and let me just show you what this means. I'm gonna give you uh let me show you something. Let's see. All right, I'm going to show you this. Let me share something with you guys. It's a video. All right, as a matter of fact, no, I'm going to show you from here.
Sir, that's how it decays each time it's cut by half-life. Like you see,
Half-life is a concept that can take a while to get your head around. But once you have,
Yeah, what are you saying, Janari?
sir, I was saying that just that's what it means by decay. Like when it comes from 10 gram to the 5 gram, that's when it decays.
Yeah, yeah. So half life is dependent on the decaying of atom. Yeah.
Just like they say, if it falls on tails, that means it decay and should be removed.
Right.
But
Right.
if it falls on it,
All right. So let's bring up this
half-life. Half-life is a concept that can take a while to get your head around. But once you have, it's a fairly simple idea. So when we look at radioactive nuclei, it's impossible to know exactly when one atom will decay because it happens spontaneously and at random. But we do need some way of knowing how the amount of radiation emitted by a source, which may contain millions of nuclei, will change over time. And this is where half-life comes in. When we look at a source containing millions of nuclei, we can think of it like a bag of coins. If we look at one coin, there's no way of knowing if it will land on heads or tails when we shake the bag.
All right, everybody was seeing that?
Yes, sir.
Everybody could hear it?
It was echoing.
It was echoing.
Yes, sir.
I guess. All right. It was. If it was echoing, I think the mic would have to be muted. All right. While it's playing. Now, if it's echoing, then I will let me see what's happening. Probably my microphone.
There was a thing come up, sir, before I log into class. It says if it's echoing, you should plug in headphone or earphone or something.
Right. So yeah, they do. All right. Did say that. So let me just go back again.
Half-life is a concept that can take a while to get your head around. But once you have, it's a fairly simple idea. So when we look at radioactive nuclei, it's impossible to know exactly when one atom will decay because it happens spontaneously and at random. But we do need some way of knowing how the amount of radiation emitted by a source, which may contain millions of nuclei, will change over time. And this is where half-life comes in. When we look at a source containing millions of nuclei, we can think of it like a bag of coins. If we look at one coin, there's no way of knowing if it will land on heads or tails when we shake the bag. But if we look at all the coins in the bag, we know that roughly half should land heads and half should land tails. So if we have 100 coins and they all start as heads or stable nuclei, after one half-life or one shake of the bag, roughly half or 50 of the coins should have turned to tails. Let's have a go. And we see that's happened. So we say the ones that turn to tails have decayed. Notice we still have 100 coins, but now only 50 are unstable and are still capable of decaying. So let's let another half-life go by. Let's shake 50 remaining heads, and we find now we have 25 coins left on heads. So the number of unstable nuclei have halved again. And if we do this a third time, the three half-lives, we find the number of heads decreases again by half, now down to 13 coins. This is exactly how it works with radioactive nuclei. And we actually define the half-life as the amount of time it takes for half the number unstable nuclei in a source to decay. Now that could be down from a million to 500,000, or it could be down from 10 to 5. It would still take the same amount of time for the same source. So let's look at a radioactive source. Let's look at carbon-14, and we'll represent the unstable nuclei as red, and the stable nuclei as yellow. Okay, so carbon-14 has a half-life of 5,700 years. So at time equals zero, all the atoms are unstable. But as time progresses, nuclei start to decay at random until at one half-life, 5,700 years, half of the nuclei have decayed and are now stable. As time carries on, nuclei carry on decaying, but it's happening less often until after two half-lives, the number of unstable nuclei are halved again, leaving only 25% of the original unstable nuclei remaining. As we progress along, we can see that the number of decays decreasing further, or the activity of the source is decreasing as time goes on. Actually, we can also say that half-life is the time taken for the activity of a source to decrease by half. So finally, as time is progressing, we get to 6 half-lives, and only 1% of the unstable atoms remain. And this has taken us 34,200 years. Now let's quickly look at another nuclei, iodine 123. Now this has a half-life of only 13 hours. So it will still take 6 half-lives to reach 1% unstable nuclei, but it will do this much quicker in only 78 hours. So What are the key points to remember? Well, we need to remember that nuclei decay spontaneously and at random. And it's impossible to know when this will happen for individual nuclei. So instead, use the concept of half-life, which is the time it takes for half unstable nuclei to decay.
All right. All right. So that's it, guys. Do you understand what that video was about, guys? All right. Who is that? All right. So there you go. All right, guys. So that's pretty much it. So when you guys gonna carry out this lab, this is the format that you will use. All right. And it will be, as you can see here, let me just zoom out so you can see the outline of it. So you're basically going to, so there's a link. There's a link here, guys. You see this at the end of the lab? Everybody seeing that?
Yes, sir.
All right. All right, good. So John's same backstage. All right. So that's the link you're going to use to carry out this lab, guys. All right. So what you're going to do here, when you go on this link, you're actually going to see this video. And it's going to be, well, there are actually two videos, but then this is the one that you're going to follow here.
Hello. Today we're going to be looking at the graph of an exponential decay relationship. We're going to look at it by using pennies. You will need today a cup full of 100 pennies, a pencil, the worksheet, and the graph that correlates to the activity. So let's start the experiment by having the 100 pennies in the cup. The first thing you're going to do is you're going to dump out all your pennies. And whichever pennies landed tails up, those are the ones that you were throwing away. So you need to put all the tails to the side of your place. So I have 1, 2, 3, 4. Once you get rid of all the tail side pennies, you are now going to count how many there are. So 1, 2. So I have 58 pennies remaining. So on my worksheet, after my first toss, I have 58. So I'm going to put 58 on my paper. Just so we know that we had 100 pennies to start with. You're going to take those 58 pennies or how many you have, and put them back in your cup. And you're going to repeat the process until you are left with no more pennies. So after you are done with the experiment and all your pennies facing tails up, you should have a full table of data. My data shows that it actually took me 10 tosses to get to zero. Your data might show something different. So now we're going to show the data on a graph. So you need your graph paper. And I labeled my axis. My x-axis is your toss number. Your y-axis is the number of remaining pennies. You should go by 5s on your y-axis and 1s on your x-axis. And now you're going to your coordinates. So at toss number 0, you had 100 pennies because you started the experiment. So you're going to put a dot at 100. And now for my data, at the first toss, I had 58 remaining. So I'm going to plot my point at 150. You will probably need to estimate the best when you are drawing the dot in the middle of two numbers. Once you do all your dots, connect your dots. And it should make this nice curved shape. So on your other paper, it asks you to describe the patterns suggested by the graph. So if you're looking at it, you probably could see that it is decaying, it is decreasing. And if you look at the numbers of your data, you could say that after every toss, about half the pennies will be tails up. And as time goes on, it gets less steep because you are putting in more or less, you're putting in less pennies in the cup every time. So the graph of an exponential decay relationship is a curved shape starting at a high y-intercept value and going down to the right at a low value on the x-axis. Thank you for watching. I hope you will enjoy the video on exponential decay graph.
All right, guys. All right, so everybody saw that, right? So again, for her experiment, I wasn't taking track of what her values were, but certainly I think when she did the first row, it was 58. So when you watch the video, you can go and find out those numbers that she had quoted, or you can do it by yourself. You can actually do it. Anybody have like them 25 cents or 10 cent coins at home?
No, sir.
No. You have $1 coins.
Yes, sir.
Well, you can use $1 coins. Yeah, $1 coins can work for this one. So you and then you don't have to have 100. That's the thing. So don't think that because you see 100 here, you don't have to have 100. This can work for 50. All right, I just put in 100 because if we were doing it face to face, I'll try to find 100. But certainly you just need like 50 or more. Janari says his grandmother have 10 cent coins. All right, that's cool. Yeah, that's cool. And they were actually they were saying that comments are lagging behind. Yeah, hush they were. Sorry about that. Probably some internet issues there, the delay. All right. And she was definitely participating here when she said the grams actually measures mass. So yeah. All right, Deborah, shout out. Hear you loud and clear there. All right. So guys, all right, we have about 7 minutes remaining. So guys, so go and attempt this lab and let me know how it work out. All right. Put your results in the table. And you can send it to me through WhatsApp and I can look at it and advise you what to do from there. Everybody understand that?
Yes,
Yes,
sir.
sir.
All right. So sir has given you 5 labs up to this date. And so by the end of April, we should increase that number towards close to 10 as possible. Let's see how many we can do. All right, today is what, Tuesday? All right, so maybe on Thursday now, we should be doing well. I should be continuing on this one because this lab is even it has more details for you to do as well. Look at that. Actually, you have these things to define. So I'll basically go into the graph for next class. So you guys, I expect that you come to class with information, with the data. All right, how many coins you use, and how many remain after you put it in a cup or some container and shake it up and throw it. You know that's the idea. So come to me with the information, guys, and then we work on the graph from there and show you how to do the calculations that you're seeing on the screen because that's where most of the marks are obtained. 10 marks for the graph itself, right? And you see that big and bold 10 marks over here. All right. Calculations value 6 marks. So this lab is heavy, guys. So you guys have to do well on this lab because it's gonna affect your evening exam grade. These labs that are marked for AI, as you can see. This lab is marked for AI. Anything marked for AI definitely affects the exam grade. Um, very much. So you want to do well on those type of labs. All right. So let's see if I'm ignoring any comments here. Yeah, did I? There is a shout out to Deborah. I hope she's still there. I hope Marlon is still there. And I hope as well. All right, so Giovanni is here. All right. Let me see. All right, so I have not seen the Chanel. Don't know if she's commenting. Don't know if she's watching. Let's hope she's there. Last thing I heard from her was she was saying it was working, but then um the site is working, but then she doesn't seem to be working. So wonder where she is now. All right, guys. So any questions here?
No, sir.
Okay, so yeah, Marlon is there. Marlon Brando. Oh yeah, that famous
No,
actor.
sir.
Back in the- All right, that's good. Um, all right, so that's it for today's class, guys. So I look forward to seeing you guys on Thursday. Remember, fill out this table, guys. Fill out the table. Do the lab on your own. Find some kinds or something that can work. And guys, bear in mind that the kinds need to be the same. So you can use 10, you can use some 10 cents and some 25 cents. That won't work. It has to be, if it's 10 cents, it's 10 cents. So um don't try and make up the number to 100. If you can only find, let's say you can only find even 40, right? 40, 10 cents, 40, $1 coin, but they have to be the same kinds, guys, right? Kinds must be the same, right? So remember that. All right. So do you have access to coins?
Yes, sir.
All right. How about you, Michaela? Do you have coins? Dijane?
Yes, sir.
Okay, you have coins. All right. Um. All right. Kalia, you have coins. January had said his grandmother have. Let's just see. Kalia, you there? All right. So let's see. January says going big sum from the neighbor. All right. All right, guys. So yeah, so this experiment is all about coins, guys. Get some coins, put them in a cup, shake it up, and then where you don't know any coins that land and tails, you're going to remove them. All right. You're going to remove them and put back the ones that are on heads. You're going to put those back in the cup and do the same thing again. All right. So and keep putting them in the cup and remove any kind that lands on tails after you throw them out. All right. So hope that's clear to everybody. All right, guys. So that's it for tonight's class. Thanks for coming out. And if you have any questions, guys, just use the group and ask those questions. All right. So
Yeah, yes, sir.